Today is a big day for the physics department and for MIT. Professor Frank Wilczek was sharing the Nobel Prize of Physics for his seminal work when he was a graduate student on quantum chromodynamics. We are now ready to tackle the normal modes in continuous mediums, and I will do that starting first with a string which is fixed at both ends. So one way you could do that is you can go back to the results of last lecture when we had capital N beats, and you can make n go to infinity. And the shapes that you get for your continuous media for the strings when they're fixed at both ends are sinusoidal motions. This would be the first harmonic, the lowest frequency, and then you get higher harmonics with higher frequencies. The question now is, what are those normal mode frequencies for those continuum media? And I will derive these today, I will derive these normal mode frequencies using a different approach than the n go to infinity route. And I'll find the same result, of course. So imagine that I have a string here, and the tension is T, and the mass per unit length is mu. And I wiggle one side, and I generate in there a wave. So I move this up and down with angular frequency omega, and I do that with an amplitude A. I will then generate waves, whereby this is what we call in physics the wavelength. That is the distance that the disturbance travels in one oscillation time. If I call this the positive direction, this wave will propagate with speed v in that direction, and we know what v is. V is the square root of t divided by mu. We derived that last time. And so y as a function of x and t, y being in this direction, x being in this direction, is then an amplitude A times the sine, or if you wish, a cosine, that's fine with me, times 2 pi divided by lambda times x minus vt. Let's first make t equal 0. Then you see what you have here, the sine 2 pi over lambda times x. If you take x 0, then you find 0. And if you make x larger by an amount lambda, you get 0 again. So that's why lambda is called the wavelength. The pattern repeats over a distance lambda. Clearly, this must be a solution to the wave equation, because any single-valued function I told you, which is a function of x minus vt, satisfies the wave equation. And so this one does too. Now lambda is v, which is this v, times the period of one oscillation, for which I will write a p today, not a t, because I don't want to confuse you. And that p is obviously 2 pi divided by omega. This is my omega, with which I am shaking. And so omega, which is then my frequency, is 2 pi times v divided by lambda. I will introduce, for 2 pi divided by lambda, a new symbol, which I call k, which is called the wave number. It has dimensions meters minus 1. This is done in most books. It is unfortunate that French calls k 1 over lambda. It's not his fault, because in the old days it was always done that way. I will follow the convention of Becker, Fehr, and Barrett, and I will call k always 2 pi over lambda. If I use that new k, then I can rewrite this in a form that you see very often, but there's nothing wrong with that form. That would now be a times the sine of kx minus omega t. Notice the 2 pi lambda over lambda becomes k, so that is kx, but omega is always k times v. And so this form is nice in the sense that if you have these two numbers, you know immediately what the frequency is, that's non-negotiable, and you know immediately what the wavelength is. It's 2 pi divided by that number, and you even know that the ratio of those two, omega divided by k, is your v, which is that v. So it's a nice way of writing things down. Now I'm going to not only generate a wave on this side that moves in this direction, but I'm going to generate one that goes in this direction. And then I want to see what they do together. And so this is now the wave that goes in the positive x direction. I call that my positive direction. And now I'm going to have another one, y2, xt, same amplitude, same frequency, therefore same wavelength, but now it's going not in this direction, but it's going in this direction. Notice there's a plus here, but there is a minus there. And so I want to know now what the sum of these two is, because one is going like this, another one is going like this. So I want to know what the superposition of those two waves do. And so y, which is then the total displacement, is y1 plus y2. And so I get the sine of alpha plus the sine of beta. That is twice, so that becomes 2a times half the sum, the sine of half the sum. Half the sum becomes kx times the cosine of half the difference. Half the difference would be minus omega t, but minus and plus for cosine is the same thing, so I will just write down cosine omega t. And this now is a very unusual wave. All the spatial information is here, so this is all the spatial information, and all the time information is here. And so whenever this sign is 0, if the x is such that the sign is 0, it's tough luck, then that location x never moves. The cosine omega t could never make it move. It always stands still. We call those nodes, and I will show you, of course, some examples. This has a name, a very nice name. It's called a standing wave. Whereas those that I have there, we call traveling waves. Now I'm going to make the string fixed at this end, and fixed at this end, well, I may shake it a little bit here. You will see a demonstration of that. And now, at this x equals 0, and at this x equals L, I now have boundary conditions that I have to meet. Y cannot be anything but 0 there, because it's fixed. And so I now demand that at x equals 0, and at x equals L, that y must become 0. And so the only way that that can be done is that you only allow certain values for k to exist. And those values for k, which I will now give a index n as in Nancy, which is going to be the normal mode, n equals 1, 2, 3, 4, is now going to be n pi divided by L. Clearly, if x is 0, okay, we're here. If x equals 0, then surely we are here, then the whole thing is always 0. That's not an issue. But you see now, if x equals L, then you get n times pi. And so again, the sign becomes 0. So I've met this boundary condition at this point cannot move. So lambda of n, which is 2 pi divided by k of n, that's the way that I defined k of n, then becomes 2L divided by n. N being that 1, 2, 3, 4, 5. Omega n, which is always k of n times v, therefore becomes n pi v over L. And the frequency in hertz, if you prefer that, is 2 pi smaller, would become NV over 2L. And so what are you going to see when you plot this function, this standing wave function? Well, it depends on the n number. Let's take n equals 1. And so the length is L. If you plot that sinusoid for n equals 1, it looks like this. And then the cosine term will make it do this. That's the task of this cosine term. The sine term is just this thing, which would then have an amplitude that could be different, of course, for the different modes, but it would be this amplitude that you see here. We call this one the fundamental. It's the lowest normal mode, but we also call it the first harmonic. I will do both. I will sometimes refer to this as a fundamental because I'm more used to that, but I will also refer to it as the first harmonic. Lambda 1 is 2L. It's just staring you in the face. In order to make a full wave out of this, you have to add this. So lambda 1 is 2L. And of course, when you look here, lambda 1, 2L divided by 1. That's exactly what we had there. So now we go to n equals 2, which is called the second harmonic. So let me write this down. So this is called the fundamental, which is also called the first harmonic. And this is then called the second harmonic, whereby the point in the middle stands still. And then the cosine term will make it change shape like this. It is unfortunate that there are books that call this the fundamental and this the first harmonic. That's enormously confusing, because now you have to start from 0, which is the fundamental, and then n equals 1 is the second harmonic. I will never do that. This is always for the first harmonic. This is always the second harmonic. And so for n equals 2, you see immediately that lambda 2 is simply L. And that's exactly what you see here. And then you can put in the third harmonic, and I will demonstrate this very shortly. So here you have an omega 1, and here you have an omega 2, and they follow this pattern. Omega 2 is exactly twice omega 1. Because when you make n equals 1, you have omega 1, and when you make a 2, you get twice that much. So now you see that the ratios omega 1, omega 2, omega 3 relate as 1 to 3 to 4 to 5. And so you can also write down here then that omega n is n times omega 1, and therefore that f of n, which is the frequency in hertz, is also n times f1. So it's very easy to think in terms of the series of these harmonics. They're also sometimes called overtones. When we talk music next Thursday, I will often use the word overtone. So if the lowest frequency in this mode were 100 hertz, then the second harmonic would be 200 hertz, the third harmonic would be 300 hertz, and so on. Now when I'm driving this string at one end, I will have a wave going in and have a wave coming back. That is exactly the recipe that I need for a standing wave. I get reflection here, and so I have one wave going in and I have one wave coming back. And if I drive these at these discrete frequencies, which are set by the boundary conditions, then the system will react very strongly, will go into resonance. You build up a huge amplitude because you keep feeding in waves and they keep coming back, so the whole thing starts building up. And that is the idea of resonance, and resonance and normal modes are one and the same. So that's the normal mode of these strings fixed at both ends. We also refer to them sometimes as natural frequencies. These points here have a name. They're called nodes. So this is a node and this is a node. And these points here, also here and here, the ones that have the largest amplitude, are called antinodes. In Dutch we call them tummies, very strange. We call them buiken. Buiken is this. So the boundary condition leads to discrete values of the resonance frequencies. And if this were quantum mechanics, we would call these eigensolutions and eigenstates. So if you want to write down now the situation for your nth mode in its most general form, then you would get y as a function of x and t in the nth mode would have its own amplitude, a of n, whatever that is. You can pick that for different values of n. And then you have here the sine of n pi times x divided by L. And here you have the cosine of omega nt. That then meets the boundary conditions for two fixed n's. And any linear superposition, any combination, various values of Nancy n and various values of a will satisfy the wave equation. So this string can simultaneously oscillate in a whole series of these normal modes. And when we do music next Thursday, you will see that actually. I will demonstrate that to you. What I want to show you now is that if I take a string, I need again assistance. Even though it has spring-like qualities, we will treat it as a string. Then I will show you that if I drive this at the end at the proper frequencies, that I can generate the resonances and I can make you see the normal modes. So who is willing to assist me this time? You were dying last time also, right? But Nicole won the battle then. Okay. So hold it in your hand firmly. Just walk back and do nothing. Just walk back, walk back. We need a little tension on there. Okay, that is fine. So I'm now going to wiggle this. This is really a fixed end. You will see when I hit resonance that my hand is hardly moving at all, because I keep pumping waves in and they keep coming back at me and the amplitude will build up. And then I have to search for these resonances, and when I hit one, I know I hit one. You will see why I know it. I feel it in my stomach, I feel it in my tummy, I feel it in my brain, in my hands. My whole body knows I hit resonance. And you will see that. Okay, there we go. This is the lowest mode. This is n equals 1. And notice that my hand is hardly moving at all. So my hand, for all practical reasons, is really a fixed end. So you get that solution. So I will now try to find the second harmonic, which would end up then as a node in the middle, in addition to nodes at the end. Is that it? Yeah? And again, when I hit that resonance, which is a normal mode, notice that my hand is hardly moving. And boy, do I feel it. I really know that I am on resonance. I can try the third one, in which case you would see two nodes in the middle and two at the end. Is this the third one? Wow, I'm good today, am I not? You see? Very clear, these points stand still. The normal modes. Oh, you're not supposed to do that. Oh man, you're ruining my demonstration. So now I will try to generate the highest frequency normal mode that I can. And so you count the number of nodes in the middle. And if you find 5, then that's the 6th harmonic. I think I can do better than that. But it's not so easy to get a very high frequency, so you do nothing because you would really ruin it. Yeah, I'm getting there. Got it. Oh my God. No. You shouldn't have moved, you see. No, it was not your fault. I'll try it again. I got another resonance. Count, please count. How many did you see? 5. I counted 12 nodes in the middle. What is your name? Oh. All right. So this is the way it works, that you see normal mode solutions, which either result which result in standing waves, and the demonstration speaks for itself. I have here a rubber hose which we are going to excite in the fifth harmonic. Let's see how that works, whether we were close. If anyone touches the table there, then the tension changes, and immediately, of course, the resonance frequency changes, because the resonance frequency, notice, has this V in it. So the moment you change T, it's different, but it's not bad. And so now I will strobe this one for you, because you have no idea that what is happening, that it's going like this. It's going too fast for you. And so I make it easy on you. If you turn the lights off, thank you. So I'm going to strobe it for you, and then I can more or less make the rope stand still, but I can also offset the frequency of my strobe light a little bit so that you actually see the rope move very slowly. So I can purposely give the strobe light a slightly different frequency. So that's what I'm doing now. You see, it's a slightly... So you have no doubts anymore about the fact, no doubts that indeed, if the middle goes up, the one on the side goes down, and vice versa. What I can also do, to turn this into a work of art, if I can turn this one off again, yes I can. I can also, I worked with an artist who actually liked these things a lot. So I can also strobe it twice as often. So this is actually, the frequency of the rope is about 9 hertz. So my red light was close to 9 hertz. The green light is 18 hertz. And a little bit off. So now you see it twice per oscillation. Of course, to make it really wonderful, to make it very sexy, I can do them both simultaneously. So now you see the red one doing its own thing, and the green one doing its thing. And what I find interesting, it may not work for you, but there are moments occasionally that the red exactly overlaps with the green. When that happens, I see white light. Let's see whether we can have a case like that. It can only... Yeah, there was it, at the bottom. Did you see it? It's white. It's really amazing. And again, at the top. All right. So, you can have some light again. Thank you, Marcos. I can now do the same thing for sound. These were transverse waves, but there is nothing wrong with doing the same thing for sound, in which case you would have a tube which has a certain length L, say it's closed on both sides for now, and I can now generate in there pressure waves, make the air column oscillate, and the air particles in the lowest mode, all I have to do is what is here in the y direction, that is a transverse position, I now have to offset the molecules of the air in the x direction. So this is the x direction, and the direction in which they move is in the x direction. But the displacement I will call psi, how much they displace from equilibrium. So in the lowest mode, that means in the fundamental, in the first harmonic, in the middle the motion would be very large, like the y is very large, and then it's a little smaller, and a little smaller, and here it would stand still, and here it's a little smaller, here's a smaller, and here it stands still. So therefore, in terms of psi, which is the position of the molecules, this would be a node, and this would be a node, and this would be an antinode in the case of the first harmonic. And so I could write down that psi in its nth mode as a function of x and t is then effectively the same as my y that I had before, except I have to replace y now by xi. So I give it some amplitude, a of n, then I get the sine of n pi x over L, and I get the cosine omega n t. So the equation is completely identical. However, keep in mind that omega n, which is this value, which is n pi v over L, that is no different. That is again n pi v over L. But v is now the speed of sound. It's non-negotiable. V is 300 meters per second, and you're stuck with that. And that has major consequences, as I will show you Thursday, for the design of wind instruments. Whereas with string instruments, you can manipulate V, and you can change T and mu. You can make the tension in the strings larger or smaller. You do not have such an option with wind instrument. The only thing you can play with is L. So this is the approximate speed of sound. More often than not, do we express the standing wave in case of sound in terms of overpressure. So we don't look at the displacement of the air molecules, which I did here, which is psi, but we want to know where the pressure is larger than 1 atmosphere and where it is lower than 1 atmosphere. It's the same idea, but it's very often done. Now keep in mind that if these particles flow in this direction and pile up here, that the pressure here becomes high and the pressure here becomes low because the particles move away from it. So that means where you have a node in psi, you always have an antinode in pressure. So these are the locations where the pressure becomes high, and the pressure here, the overpressure over and above ambient, is zero here. There is nothing that prevents the pressure from building up. These particles are free to move. And so if you write it down in terms of P, which is now overpressure, it is not the total pressure, but it is what is over and above 1 atmosphere, then you get some amplitude in pressure. I give you just a P of n, and now I get the cosine of n pi x over L, and then I get the cosine of omega nt. And you understand now why you get the cosine, because the antinodes are now here at the ends, which is the consequence of the boundary condition. If I drew a curve, if I made a plot of the pressure, I will do it here so that it doesn't become too cluttered. So here is now 0, and here is L. If I put here the pressure, then in the first harmonic, the fundamental, here is a pressure node in the middle, where there was an antinode for psi. There is now a pressure node in the middle, and then the pressure will change in this way. So this is now n equals 1. So the pressure here at one moment in time is high, then it's 0 here, and then it is low here. It is below ambient pressure, and that, of course, is changing with time, with the cosine omega t term. And again, you see that lambda 1 is, of course, 2L. There's no difference there with the string. I can demonstrate this to you in really a very, very nice way. I have here a tube which is closed at both ends. And so here it is. But in one end, I have a piston. And so I can change the length L. You'll see in a minute why I like to change that length L. We're going to drive the inside with a microphone. So here is a microphone. And we're going to do that with a frequency. We really wanted to do 803 hertz. But 803 hertz has a rather long wavelength. I wanted to have it shorter, so I do it 3 times 803. So the frequency is 3 times 803 in your honor, which is 2409 hertz. And so the wavelength lambda, which is V divided by the frequency, that's correct. The wavelength lambda equals V divided by the frequency is then very roughly 14 centimeters. So that gives you an idea It's about this much. In here, we have a microphone that we can move in and out, and a microphone measures pressure. So it has a membrane, and so it's sensitive for pressure. And this microphone is connected to a loudspeaker, so you can hear it. We also show it to you, the signal of the microphone. We will show it to you as we record it on an oscilloscope. If I put the microphone at a pressure node, you hear no sound. And if I move it to an antinode, you will hear sound. I will create in here pressure nodes, 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 which are always half a wavelength apart. Think about that, why that is. You see here, the nodes are half a wavelength apart. The same would be true for sound. I'm then going to put this microphone somewhere at a node that we all agree you hear almost no sound and we see no signal from the oscilloscope. And then I'm going to move it back and search for 1, 2, 3, 4 nodes. And then I know that this distance is going to be 2 lambda. And I have therefore measured lambda. And the amazing thing is, which actually surprised me, that you can do that to an accuracy of about 1 millimeter. It is so enormously clear when you are at a node that if you move your mic by 1 millimeter, you can really see that you're no longer at the node. So we will know lambda probably to 1 millimeter accuracy. Once we know that, the speed of sound is lambda times f. But we know what f is. That's known to one part in, we couldn't be off by more than 1 hertz, so that's very well known. And so we now have a measurement of the speed of sound. High degree of accuracy, we measure the speed of sound. And so we catch 3 birds with 1 stone. First of all, I can show you the nodes and the antinodes, so you see how they build up there. And then, at the same time, we can measure the speed of sound. The only reason why we make this end movable is that as I move it and bring the mic first at a node, I can make sure that the length is just at resonance. And so that's just my beginning to make sure that the node is as close to 0 as it possibly can be. And so if we now get the image up there, and then I think we are going to get the light situation like this, and going to turn on the sound. Here is the sound. I can turn up the volume so that you can hear it better. Is the scope connected, Marcos? Oh yeah, of course, thank you. I didn't connect the microphone yet. It has a switch. Okay, let me first move the, oh, it's awful. This is 2409 hertz, by the way. I'll turn it down a little. Is that better? Okay. So let's first move it around. Let's first bring it to a node. Boy, that's nothing left anymore, right? And now I'm going to change L. Okay. I think this is, I cannot do much better. So what L is not very important. I set L so that I think the system is at resonance in a mode that you can calculate if you know how many nodes there are. So I'm going to search for a, well, here you see the antinodes, by the way. You see that? I'm moving it in now. I'm moving it further that way. And here you get to another node. You see that? Isn't that wonderful? And I go again to an antinode. And here comes another node. And this node I'm going to measure, the position. I have a ruler in there. And the ruler gives me the position of the mic. And this one is 52.8. So 52.8 centimeters is this position here somewhere. And I can put a mark here for you, not that it will help you very much, because my accuracy is 1 millimeter, and this is a very crude way. So now I'm going to pull it back. You're going to see an antinode, and you hear it. A little bit more sound. And you're going to see a node, that's number 1. This is node number 2. Node number 3. Node number 4. And I'm going to look, and I'm going to look now at the reading, and I read 24.3. So I read 24.3 centimeters. So I subtract them, that is 5, 28.5 centimeters, and this is 2 lambda. And I know this really to, I would say, to a millimeter. Certainly no worse than 2 millimeters. And there is no uncertainty for sure in the F. If you can give me the light back. So I can now calculate what the velocity of sound is. So that is 28.5. I divide that by 2. That gives me 14.25 centimeters. This was just a rough number that I gave you. And now I multiply that by the frequency 2409. And then I find 343. So V is 343, I would say, plus or minus maybe 2 meters per second. So we've measured the speed of sound to a high degree of accuracy. And of course, at the same time, you have seen this wonderful resonance normal mode behavior where you see the nodes and the antinodes, in this case, of pressure. Earlier you saw them here in terms of transverse motion. Now you have seen them in terms of longitudinal motion. There is energy in a traveling wave. If I have here a traveling wave, which is moving in this direction, has tension T, mu is the mass per unit length, then I can write down y as a function of x and t. I can give it a certain amplitude, a, times the sine, and I can write this now in many different ways, but let's write it down in this form, k times x minus vt. And we know this v, that v, let's call it v squared, is t divided by mu. So this is a traveling wave that goes into the plus x direction. Is any matter moving in the plus x direction? No. But is anything moving? Yes. It is moving in the y direction. So since these particles have mass and they are moving in this direction, there is kinetic energy due to the motion in this direction, not due to any mass that moves along. No mass moves in the direction of here. Suppose I carve out here a section dx. So this is the direction of x, and I take a small section dx. Then the kinetic energy, dE kinetic, tiny little bit of kinetic energy, is 1/2 times the mass dm times the velocity in the y direction squared. That is 801, right? Kinetic energy is 1/2 mv squared. Never confuse this v with that v. That is the velocity of propagation. This is the velocity of the string in this direction. So I can write this down. dm is obviously mu times dx. If I have a length dx here, and I have mu kilograms per meter, so I get here 1/2 mu times dx, and for this I write down dy dt squared. This is the velocity in the y direction, and I use partial derivatives because I do it at a given location for x. So what is dy dt? Well, that's easy. That's a piece of cake. There is my function. So I get an A. Then I get a K and a minus V. So I get a minus and a K and a V. And then the sign becomes a cosine. And so I get K times X minus VT. I should have put brackets around there too, but that's self-explanatory. And now I want to know what the square of this is. So I'm going to square this. Now I can calculate what the total energy is, kinetic energy, in one wavelength. All I have to do is integrate now from 0 to lambda to get the total energy in one wavelength. So I'm going to do that. I'm going to write down here now E kinetic. Now follow me closely. I have a half. I have a mu. And then I get the dy dt squared, so I get an A squared. I get a K squared. I get a V squared. And then I get the integral from 0 to lambda of this function, cosine K x minus Vt. And then I have my dx, which is this dx. That's what the integral is in the direction of x, yeah? Yeah, thank you very much. Extra course credit. What is this integral? Maybe you don't remember, but I've done this often enough that I do know. The integral of cosine square of that function is lambda divided by 2. And I leave you with that. That's a very easy exercise. And I can also take the v square out and write for that t over mu. So E kinetic now, and this is in one wavelength. This is my shorthand notation. So all I'm calculating for you now is how much is in one wavelength. So you're going to get now 1/2 mu. You get an A squared. The K squared I can write down as 4 pi squared divided by lambda squared. For the V squared I can write down T divided by mu. And then I have my lambda over 2. Well, this mu kills this mu. This 2 kills this 4 and this 2. And 1 lambda kills 1 lambda here. So now I have the final result that E kinetic in one wavelength equals A squared times pi squared times T divided by lambda. Now, if you look at this and you ask me, is that obvious? I would say, not to me. There is a T, there is a lambda. My goodness. And I can also cocktail the whole thing. I can get the T out and get a V back in again. And I will admit that I don't have a very good feeling for this function, except for one. I do know that always the energy in a wave is always proportional to the amplitude squared. You're going to see that when we do electromagnetic waves in 803, it's always proportional to A squared. So that's the only one for which I may not have a feeling, but I know it's got to be there. And the rest, I will leave you with that to see whether perhaps you can talk yourself into understanding why you see the symbols where they are. Now clearly, there is also potential energy, because it takes energy to make that straight line into a curve. And that means work that you have to do. You have to squeeze, to stretch it. There's a tension and you have to stretch that. And so you have to do work to just get the shape. And that is potential energy. And the potential energy per wavelength, which I want you to do on your own, it's worked out nicely in French, I will not do it today, happens to be exactly the same as the kinetic energy, which is by no means obvious. So the potential energy per wavelength is the same as the kinetic energy per wavelength. And so what that means then is that the total energy in a traveling wave is twice this. Kinetic energy plus potential energy. That is the total energy in a traveling wave. I can now make you see, in a nice way, an energy balance to compare traveling waves with a standing wave. If I have a standing wave, and the standing wave is like this, and I do this, I look at this picture at the moment that the wave stands still, that Vy is 0, so it goes like this. That's a standing wave, you've seen that. I do it at this moment, there is no kinetic energy. There is only potential energy. A little later there is only kinetic energy and there is no potential energy. And a little later there is only potential energy and no kinetic energy. If I pick that moment that it stands still, then I know that that's the total energy. Because it's only potential, but it is the total. In other words, for a standing wave, if this has an amplitude A, it must be the same potential energy as you have in a traveling wave. Because it's simply due to the fact of the shape. It has nothing to do anymore with motion. So for a standing wave, E total must be that number. Whereas for a traveling wave, you have kinetic energy plus potential energy, so you have twice as much. Now I can convince you, and that was my plan earlier today, that if I have one traveling wave with amplitude 1/2 A, and I have another traveling wave again with amplitude 1/2 A, I know that I'm going to make a standing wave with amplitude A, right? Because 1/2 A and 1/2 A, when we added them up, you got twice, here you got this 2A. But there must be a certain amount of energy in that wave that comes in, which is 1/2 A, and a certain amount of energy in this one. And when you add those energies up, you must exactly get the energy in a standing wave, because no energy was lost. So therefore, I make the following statement now, which is testable, that two traveling waves, each with amplitude 1/2 A, I'm going to compare them with a standing wave with amplitude A. There must be the same energy in a standing wave with amplitude A as there is in two traveling waves with amplitude 1/2 A. Did we follow that? Was that too difficult? Because we know that we can make that way the standing wave. Now, okay. We know that the total energy in a traveling wave is this. But we have two of them. So in the traveling waves, in two traveling waves, we have two. Then we get that 2 there, that's non-negotiable. Then we get pi squared. Then we get t, and we divide by lambda. But the amplitude A that we have there is now 1/2 A. Yeah? Is that too difficult? I give it an amplitude 1/2 A. So now I get 1/4 times A squared. So this is the energy in two traveling waves. Do we agree? What is the energy in one standing wave with an amplitude A? Well, we have the answer here. In a standing wave, all the energy must be A pi squared t divided by lambda. Look at it. They are the same. This 2 and this 2 and this 4 eat each other up. Just a second. So you see the consistency, I'll give you a chance, that two traveling waves making up one standing wave, in the exercise I did earlier, that indeed energy is conserved. The energy in the two traveling waves with half the amplitude gives you then a standing wave with A. Yes? A squared. Thank you very much. Always A squared. And what I said, energy is always A squared. Thank you very much. if I generate traveling waves, I, Walter Lewin, start shaking strings, or some other instrument is making traveling waves, then there is an energy flow in the direction of propagation. Because these wavelengths keep moving, these waves, and so there's an energy flow. There is no mass flowing. Oh, there's energy flowing. The mass is only doing this. And so therefore, if I generate a certain amount of energy, then I need power to do that. Namely, power is energy per unit time. And so I can now very easily calculate for you the power to generate a standing wave. That is utterly trivial, because the energy in the standing wave is 2a squared pi squared t divided by lambda, and all I have to do now is to divide it by the time that it takes me to generate one oscillation. So that's the period of the oscillation. And the period of the oscillation, I try not to put too many p's in there, and I hate to call it t, so the period of the oscillation is the same as 1 over the frequency. And 1 over the frequency is v divided by lambda. So therefore the power is simply the energy that I'm generating, and v divided by lambda is the same, is 1 over the period of one oscillation. Energy divided by period, the time that it takes to make one oscillation, is per definition power. And so then you get the result here, you get a lambda square here, and you get a v there.
There should be 2 there because this is a standing wave.
Excuse me?
This is a standing wave, right?
This is a traveling wave. It's good that you asked that. I am generating a traveling wave. I have to do work. For every wavelength that I produce, this is the amount of work that I have to do. Do we agree? There is energy in the potential energy, because I have to give it that shape, and there is kinetic energy because it moves. If I generate this amount of energy, what is your name? James? James, if I generate this amount of energy, and I divide that by the time that it takes me to generate that energy, I get the power, the average power that I have to put in. It's really average power. And so I have to divide this by the period of my oscillation, the time that it takes to make one oscillation. And that is lambda divided by v. That is the period, and so I have to multiply this by v divided by lambda. So this is really what we call frequency. And so now you get the power. And so you can move energy from one point to another without any mass moving. All right. This is an ideal moment for a break and for a fatherly talk. I've had some very interesting email exchanges with quite a few of you. And as a result of that, I have decided to lower the 10% of the mini quizzes to 5%, and to raise the homework from 10% to 15%. I think that will make probably most of you happier. Though not all, some of them thought it was fine, but I think most of you will be happier. And I will make that change this afternoon on the website, so you will see that reflected when you look tomorrow morning. I will also be more careful that the people here in the front row don't have 5 minutes and the people in the back maybe only 1 minute. And so therefore, I will make sure that each one of you from now on has the same amount of time. And so what I'm asking you now is not to start until everyone has, and then I will blow the whistle, and then I will give you 5 minutes. So if you start handing this out. Okay. I'm now going to change the boundary conditions, which is something that you will need very much for your problem set. here is a string, mu1, v1, and here is a string, mu2, v2, and obviously they are at the same tension, one string. And so v1 is the square root of t divided by mu1, and v2 is the square root of t divided by mu2. I will call this point here, for simplicity, x equals 0, that is the junction, and this is the y direction, and this is the x direction. And I'm going to have a wave coming in from the left, which I call the incident wave. Incident, I will give that an I, moving in this direction. And then there will be a reflection, which I call R. Something may come back, so that it goes into this direction, both in medium 1. This is medium 1, and this is medium 2. And then something is being transmitted into the second medium. I will give that subscript TR, and that is going into medium number 2. And that's what I want to evaluate now. Now I have boundary conditions at x equals 0. I told you earlier, all of 803 hangs together, the wave equation and boundary conditions. And that's true. The boundary condition is that at x equals 0, y1 must be y2, unless the string breaks. So the y right here must be the same as the y right there, otherwise there would be a break of the string. But not only that, dy1 dx must also be dy2 dx. If that were not the case, there would be a kink in the rope at the junction, and a kink would mean that there is a tension here and that there is a tension here, which would give a net force down, but the junction itself has 0 mass. And so that would give an infinite acceleration. So you can never have a kink in a string, not even when it is connected like this with another string. So it must be something that is always fluent here. Or it could be like that, or it could be like that, but it cannot be like this. And so that's then the condition that the derivative, the spatial derivative from the left must be the same as on the right side. So let us start with an incident wave. Comes from the left. And so y1, yi, I, is incident, has some amplitude a of I, that is the amplitude of the incident one, times the sine, and I'm going to write this now. I can write that in many different ways, but I'm going to write this now as omega 1t minus k1x. That's clearly a traveling wave that moves in the plus direction, because the signs are different. And now I have a reflected wave, amplitude A reflected, times the sine, obviously the same frequency, but now I get plus k1 times x. Notice the difference in sign. This one is going this way, this one is coming back. The amplitudes are different, but the k's are the same, because the wavelength in medium 1 is the same. The k is 2 pi over lambda, and that wavelength is not going to change for this wave as it is for this one. And so now I get the transmitted one is amplitude transmitted times the sine of the same omega, because if this junction shakes up and down with frequency omega, that's the same for both media. So omega is a given. You can't change omega. You can't say omega is different from the right side than it is for the left side. In other words, omega 1 is V1 times K1, but it is also V2 times K2. It's the same omega. And so I get here minus K2 times X. So this goes into the second medium. The minus sign indicates it's going in this direction, but the K2 is different because the speed is different, because V2 is different from V1. And so with the same frequency, I get a different value for K. So if now I go to my boundary conditions, y1 equals y2, which you see here, then I get there that a of y, a of I, so x equals 0, at any moment in time, I must meet that condition. So a of I plus a of r must be a tr. If not, then the string would break. I can now take the derivative of my function, dy1 dx. And so when I do that, I get the first one is going to be an a of I, and then derivative against x gives me a minus k1 here. And then I get a cosine of omega 1t, because x was 0, remember. So I get a cosine omega 1t, but each term will have a cosine omega 1t. So I will dump all the cosine omega 1t's. So I go to my next one, which gives me now plus a of r times k1. And that now, this is the left side. This is my dy1 dx, and my dy2 dx in my second medium is now this one. Gives me a minus k2 times a transmitted times minus k2, and I dump the cosine. So this is the second equation, and you could solve these two equations easily, except you have two equations, with three unknowns. You have ai, ar, and a transmitted. And of course, you cannot solve two equations with three unknowns, but what you can find, that is the only goal I have, is the ratio of the amplitude of what comes in over what comes back. That's my whole goal. If you calculate for this one k1 over k2, and you substitute that in here, then you can replace the k's by the ratios of v's. You see that? So you take k1 divided by k2, and you get rid of your k's. So when you do that, you get a of I minus a of r times v2 equals a transmitted times v1. So that is simply combining these two. And so now all you have to do is calculate the ratios of those amplitudes for this equation, one equation with three unknowns, and the second equation with three unknowns. And what comes out of that, this is also worked out in French, what comes out of that is that the reflected amplitude over the incident amplitude is v2 minus v1 divided by v1 plus v2, and a transmitted divided by amplitude of the incident one is 2v2 divided by v1 minus v2. Sometimes I call this with shorthand notation R, reflectivity, it's the ratio of amplitudes, and sometimes I call this shorthand notation TR, which is transmittivity, the ratio of the amplitude that penetrates the second medium divided by the one that came in. So that's just my shorthand notation. We can now do some interesting examples, and you will begin to understand what is happening here. Take an example, for instance, that mu2 is infinitely large. That's a wall. So in other words, that second string is a wall. If that second string is a wall, you better believe it, that that point cannot move. The incoming wave couldn't possibly move the wall. So this is the same as what we earlier called, it's a fixed end. In other words, v2 is 0, right? Because if mu2 is infinity, then v2 is 0. So now I go to those equations, and I say, what is now r? v2 is 0. Well, if v2 is 0, I get minus 1. Hey, minus 1, that means when a mountain rolls in, what comes back? A valley. And when a valley rolls in, what comes back? A mountain. And we've seen that. We demonstrated it last time. A fixed end. And what do you think TR is going to be? What do you think it's going to be? 0. Nothing goes through. And look at it. If V2 goes to 0, TR is 0. So aren't we happy? Take now an example that V1 is smaller than V2. In other words, mu1 is larger than mu2. When we have a case like that, notice that R is always larger than 0. If V1 is smaller than V2, this is a speed now, this is always larger than 0. What that means, just a second, I'll give you a chance. What that means that a mountain comes back as a mountain. Now the amplitude of the mountain will be changed, but it comes back as a mountain, because that's the plus sign. And notice that the transmittivity is always larger than 0. It never gets a minus sign. Of course it cannot get a minus sign. That you can explain to your kid brother, because if a mountain comes in here, that point is going to move up no matter what. And if this point is going to move up, what goes into the second medium is a mountain. And if this point goes down, because it is a valley, that what goes into the second medium is a valley. So it is completely logical that here you never can get a minus sign, but here you can. There was a question. Thank you very much. My goodness. Oh. Yes. V1 plus V2. Thank you very much. Thank you very much. So now, we take an example which is absolutely thrilling. V1 equals V2. That means mu1 equals mu2. That's another way of saying there is no junction. It's just one rope, all the same material. Well, if there is one rope with all the same material, do you think that anything will reflect? Of course not. So I predict, without even looking at the result, that R is 0 and that the transmittivity is going to be +1. Let's check that. When V1 is V2, this is 0. And when V1 is V2, you just corrected me at the right time, by the way. When V1 is V2, you see that this goes to +1. With the minus sign, it would have gone to infinity. I would have caught it. But you got it earlier. Okay, so now let's do a specific example whereby we give some numbers, because that's what I plan to demonstrate. So the example that I have in mind is that V1 is 2V2. So V1 is 2V2. In other words, mu1 is 1/2 mu2. If I put that in that equation, I find that R equals -1/3, and I find that the transmittivity is +2/3. That's just a matter of sticking those numbers in. And that means then the following, that if this is my incident wave, so this is now the incident one, and the incident one, say, has an amplitude 1, and is moving in this direction, that the returning one has a amplitude which is 3 times smaller, and it is flipped over, but it has the same length because it has the same speed. So suppose the returning one were here, then you would see the returning one with only 1/3 of its amplitude. So that's about here. So you would see something like this. And it would be moving in this direction. And this amplitude is 1/3. And now, what goes into that medium number 2 is a pulse with 2/3 the amplitude. So this is the 2/3 mark. So the amplitude is only 2/3, but since the speed is lower, because you notice the speed is lower, therefore it shrinks. And so not only will the amplitude be 2/3 of the incident one, but this length will only be half. And so you will see this. And this is now 2/3. And this is moving with velocity v2. This is moving with velocity v1. And this is moving with velocity v2. So that's the meaning of R and TR. There was a question here. mu1, v1 is 2v2, then mu1 is 1/2 mu2. Is that wrong? Yeah, you have a good point. Let's just remove it. Okay now? Thank you. So this now I want to demonstrate. And the way we're going to demonstrate is we're going to use this machine. And this machine allows me, this has a medium here whereby the speed is twice as high as the speed here. I'm going to generate here a mountain, and the mountain will go into that medium, and the first thing I want you to notice is that as it enters this medium, where the speed is lower, the speed is higher here than there, I want you to see two things. That first of all, the mountain goes through as a mountain. Whatever goes through must always have the same polarity. If a mountain comes in, a mountain goes through. So look at two things. The mountain remains a mountain, and it will shrink. And then later we will look at the reflection. Okay? So here, oh, we have to make it completely dark, don't we, for this? Yeah, I think that's more romantic. Yeah, that's what they like, yeah. Okay, so I'm going to generate here a mountain as fast as I can. The speed here is larger than the speed over there, and you will see that the pulse shrinks, but the mountain remains a mountain. You ready for that? Did you see that the mountain remains a mountain? And did you see that it shrinks? I need some light because I think I broke something, yeah. No problem, fixed. Okay, now we want to do something else. Now I want you to see that when I drive in a mountain, that a mountain goes through, but the valley comes back. And the valley that comes back has the same length as the incident one. That is the -1/3, remember? So the valley is very shallow, but the mountain will come back as a valley when it hits this point here. So we have already seen that the mountain goes through as a mountain. You have already seen that the pulse gets shorter. And now you are going to see that when it hits this point, that the reflection will be -1/3, so the mountain will come back as a valley. You ready for this? And there it comes. Could you see it, that it came back as a valley? Shall I try again? You see, the speed is very high. That's the problem. So it's very hard to see. I'll try it once more. Yeah, I could see that the mountain came back as a valley. In fact, what would happen if I drive a mountain in from this end? What would come back, a mountain or a valley? So if I do it from that end, the mountain returns as a valley. If I do it from this end, the mountain must return as a mountain. Shall we take a look at that? And it comes back as a mountain. I'll do it once more. I think I broke that one too, yeah. Boy. I only have one problem. And that problem is going to be your problem. And that is the following. I would like to explore now the possibility that mu2 is going to be 0. That means V2 has become infinitely high. If mu2 is 0, there is nothing here. It means there is tension on the rope, but there is nothing here. It's empty. We call that an open end. So imagine in your head that something is holding it tight. The end can move freely. That's no problem, but there is no mass there. Remember, it was like the massless string and the rod. So now, in this case, which is really an open end, there is nothing in medium 2. I can now go to my equation and ask what R is. And I will be very pleased. When mu2 is 0, when V2 goes to infinity, when V2 goes to infinity, this is +1. Mountain comes back as a mountain. All of you predicted that last time. An open end, a mountain comes back as a mountain. Yuppie, physics works. What do you think is going to be the transmittivity? 0, yeah, that's what you think. Put in there V2 equals infinity. Now that takes you by surprise. +2. Holy smoke! What is going on here? If this were true, we would have solved the energy crisis of the world. Because a pulse comes in, and the whole pulse comes back, everything that went in comes back, mountain comes back as a mountain, but there is something in addition that goes into nothing. I want you to think about this, and you may not be able to sleep tonight. And if you can't, it is not my fault. It's the fault of physics. See you next time.